how we're sharing the screen, or I can share just the slide. Leave it. Okay, fine. I can leave it like this as well. Okay, cool. Okay, let's see if this works. Yes. Okay, so it's a pleasure to be here in this beautiful building at this prestigious institution. I'm always happy to come when I manage. So today I'll say something in terms of using machine learning in various forms and shapes and purposes at CERN for our research. And okay, I need to start a bit with what we're actually doing just for completeness. So basically what we're trying to understand is the way universe works. So the way it's structured, the way it evolved from the Big Bang and so on. And an interesting point is that the universe, I mean, which we like to show is that the universe has become transparent only, well, depending on calculations, a few 100,000 years or a few tens of thousands of years after the Big Bang. And before that, we actually can't see it by looking at the sky because all the light was trapped. So the evolution wasn't happening visually, but we have to recreate whatever was going on in laboratories in terms of locally producing enough energy to get close to the, if you want, Big Bang energies or temperatures and so on, to understand and unravel a bit what's been going on. So, of course, we're still not there in terms of understanding everything. And a very good example is the discovery of cold dark matter and plus the dark energy that you can see here, which is basically the vast majority of our universe. And by dark, just as a disclaimer, we don't mean we can't see it because it's not reflecting light and so on. It's something really outside of the standard model or periodic table, if you want. So we don't know what it is. And of course, this is now the name of the game of what we would like to understand. So we do think we understand the so-called standard model with the basic interactions of physics, which sort of cover about 4% of the matter in the universe, matter and energy. So this is the idea, what we want to do. And how we want to do it, how we want to recreate the more primeval, if you want, situations, is by colliding particles and locally producing enough energy to unravel the hidden interactions in particle physics. And for that, we need colliders, right? And the biggest one currently is the Large Hadron Collider at CERN, which has been built in the early 2000s and is now operating with 4 big detectors, so CMS, Atlas, LHCb, and Alice. Atlas and CMS are the multi-purpose ones, and our group is working on Atlas since the beginning. Now, it's, of course, always a bit difficult to say how, in sort of layman details or layman words, what the performance of this machine is. But in rough, it's a 27-kilometer long ring of instrumentation running about 100 meters underground in the Geneva area, so between France and Switzerland under the border. We're increasing the energy gradually since the start of the operation, and currently we achieved the center of mass energy measured as 13.6 tera-electron volts. Now, of course, this is a physicist, particle physicist unit, so we're always asked, what does this mean in layman terms? And we came up with some analogies. So like, if you translate this into a kinetic energy, this is like a small cruise ship of 10,000 tons moving at a slow pace, like 80 kilograms of TNT. I like this one, 16 kilograms of chocolate. Or if you want the ones the Brit prefer, you can basically cook a cubic meter a ton of tea with that energy. So depending, right? But in terms of particle physics, this is quite a lot. Of course, if you go to the experiments, just to give you, this is what we can create in a laboratory, right? As a point, if we go to the astroparticle physics experiments, which for example, University of Nova Gorica participates in, you can go many orders of magnitude above this energy by observing cosmic particles. Now, of course, this is not a controlled reaction, but it's something that you can measure. So, of course, this is a complementarity, if you want, that it's, I think, worth mentioning. Okay, so I guess I admit them. Yeah. Okay, so this is basically it. The tunnel looks like this, right? This is the experiments that have been pulled apart when they were being built or upgraded so that you can a bit see the structure. Now it's all tightly packed, of course, and operating. So, of course, what we want to do is analyze the data we collect. And that's where the challenge comes in, and that's where the machine learning comes in various forms. So we actually literally produce hundreds of petabytes of data. And those hundreds of petabytes might contain something new. There is a lot that we know, and we're mildly interested in those. But above all, we want to understand what we don't, we want to find what we don't understand, or something that doesn't match our predictions. So this data then has to be basically filtered and then reconstructed, understood, processed, and so on. And to stress the point, in a timely manner, of course, we have to do it reasonably promptly. And for that, we need, of course, the best and most modern approaches that we can manage. And okay, just to give you an impression, this is a bit old as a plot. It's hard to get a newer one, but it's still representative in terms of ratios. So the data set that the LHC experiments produce is comparable to something that, for example, Google or YouTube or I don't know, Instagram store per year. And of course, it's very different data, and we have very different interests in filtering and browsing and analyzing that data. And so we need to develop our own approaches, tools, or adapt the commercial ones. So what do the collisions look like, just as an idea? So we know that, I mean, I mentioned that we have a center of mass energy of colliding particles of 13.6 tera electron volts. And this means that protons are colliding, right? And then it's the quantum mechanics plus E is mc squared. And we get a lot of particles in the final state, which we then need to, of course, recode and understand with the detectors that are built around the collision points. And this is complicated, right? If you can imagine, this is a reaction, and then we want to understand what's been happening in this particular point. So like a grenade exploding, and then you want to reconstruct everything and read the serial number sort of thing. Now, to complicate matters further, it's an interesting point where you also use machine learning now, is that, of course, we want to have as many collisions as possible, which means we're not taking one proton and the other proton and colliding them, right? That would be hopeless. What we're having is bunches, like clouds of protons passing through each other. And the more we squeeze those clouds, the more collisions we get, right? And the problem is when we don't get only a high collision rate, but we get an overlapping collision rate. So this is called pileup, right? And what we're having now is up on the order of average 70 protons colliding at the same time, and going up to a few hundred, like 100 something. Here you have 102 vertices, where you have like 100 protons colliding at the same time, and these interactions overlap. And then we have to separate those because, of course, the overlapping signals could mimic something new, but not, right? So we have to do this, and this is one of the applications where we use machine learning to separate these. And to make the story more interesting, with all the upgrades that we expect in the next decade or so, the volume of data and the complexity of data will increase with the updates of the Large Hadron Collider and the detectors. So the hardware will be upgraded, and then the software and the whole science approach and analysis and so on need to follow up on that. And it's an interesting challenge, and we're really trying to step up the activities to sort of match what we can do and optimally, of course, analyze and prepare for the future. Now, I've mentioned machine learning a couple of times, just to stress the point that this is not something really new that we use at CERN, right? I always like to give this example just because I have materials on that. It's almost 25 years ago, right? For my thesis, I already used machine learning, and I wasn't the first one at CERN doing it, right? And already at that time, we had very nice clickable tools to do feed-forward neural networks with various base, activation functions and so on and so on. And we use this, for example, to find matching pairs between different objects that looked similar, like 4 jets. So 4 jets of particles, and you need to find the right pair that was produced from a particle at the beginning. So, so this was something that we used to great effect already then. And then, of course, this is progressing now. And by now, we're using it basically everywhere, and we are thinking about using it even further. So to give you a few examples where you use the machine learning. So we use it in doing the theoretical modeling in terms of calculations and simulations of various cases. They're also looking into, theorists are also looking into things like unfolding the data, so understanding what's the theory behind it, if you want, in basic terms, and in computation of the complicated Lagrangians and so on. So it's an active field, right, which is looks promising, but we're still waiting for definite results, which we assume will come in the next decade at least. Then, as mentioned before, right, if you have multiple collisions, you want to reconstruct the collision points and remove the overlaps in these pileups, and this is something that we do. Then, of course, you have this complicated interaction, right? And you have a lot of particles being produced and so on, and then you have to decode the whole event. What was actually happening? Which reactions took place? Was it weak interactions? Was it strong interactions? Was a Higgs boson produced and so on? So we want to use this to decode the process, to understand the components and identify them. If you want to tag the different participants in this process, then we have the omnipresent noise in various levels, right? From purely electronic noise to artifacts when you reconstruct the whole process because the detector is not ideal, to anything that we can call noise in terms of backgrounds as well, right? I mean, so this is what we want to do. And in the end, we want to precisely measure what remains, right? And so reconstruct really in grand detail what we believe was happening there so that we can actually say this is something we understand or we don't understand. And for that, we have, in terms of CERN, set up various forums where we share the experience between the experiments with other sciences and so on. There is something called the HAP Software Foundation, where the whole of the software effort, including machine learning and AI, for example, now is being discussed and shared and so on. So it's an active field, and here I'm just, sort of flashing a lot of papers from Nature to internal publications to presentations in conferences and so on, just to give you an impression of how many different looks or approaches we use in doing really new physics analysis by employing machine learning in various forms and shapes. So we were very active, and by now it's become basically a practical tool for everyday use, right? But what's driving us in terms of efforts is, of course, that the industry is making huge progresses in the field because of commercial interests, and that the hardware is actually there, right? I mean, the advent of doing machine learning calculations on better and better scale is especially because we have better and better hardware, more computing power to do these complex calculations. That's why Gabriela before, for example, mentioned the Vega supercomputer that we have, that is essential for these kind of studies. So just in terms of pedagogical points, just to give a bit of a note on what I'll be describing, not to just flash numbers. So as said, right, the whole idea, if you're not aware of the neural networks, for example, which is sort of the bread and butter now of the machine learning approaches, comes from the 60s. So it's not really nothing new. I mean, it was just then propagated to great effect when the hardware became better and better, and these calculations became faster and more complex. So basically what we want to do is just use this sort of simple operations by stacking them in intelligent ways, right? And mimic very complicated neural networks. So what we employ now and study in terms of functionalities in CERN analysis is, on one hand, that we want to look at the possible topologies. So how do we stack these simple objects in a complicated form, right? Is it just simple layers that are fully connected? Is it something more complicated? And so on. I'll say a bit more about it. Or how many, in terms of complexity, how many of these neurons do we need to employ, right? The deep neural network just means that we use a lot of neurons because we can. I mean, so deep machine learning is just that, the increase of scale of the computational power. So we're looking into both of these aspects and trying to push the envelope. And then what is happening is that we're trying to take various cases that were developed, as mentioned before, in this industry, like convolutional neural networks, the recurrent neural networks, and so on, with different topologies and different connectivities between these layers, as mentioned, to find the optimal use for various use cases I mentioned before. So the most basic approach that the sort of machine learning has been used for since decades, basically, at CERN, is so-called event filtering. Now, what we want to do here is use the machine learning in a physics analysis to separate the known from the unknown, the signal from the background, right? And in terms of machine learning, this is using machine learning tools such as neural networks as classifiers. So we want to classify different types of data in different groups. For some reason, mostly historical, at CERN, we use the term multivariate analysis for machine learning approaches. So MVA is something that you'll often see in our slides instead of ML or something similar. And then, what we want to do is find some separation in terms of optimal use of machine learning tools to get sort of a score that would give a high value to unknown or new signal and a low value, low score to something that's known, like the standard model. And this is basically the typical plot we're looking into, right? That we want to see. So we want to see an optimal separation between the background on one hand, so the known, and the something new. And we have a lot of ideas what that could be, right, on the other side. So for that, we look into various options, as mentioned before. And there is a sort of a historical evolution we're trying to follow the industry. Yeah. So we started with the neural networks and then deep neural networks. So high computing power. Then we moved to the convolutional neural networks for especially ideas like image recognition that was used in industry. So we can use this for specific cases. Then recurrent neural networks. So we figured out that for some sorts of analysis, it's good to have a bit of a persistent memory, if you want, in the whole process of learning. And then the latest, greatest that is now all the rage are the graph neural networks. So we have a solution like 10 years ago in the deep neural networks. We moved to convolutional neural networks. We gained like 10%, for example, in terms of efficiency, then to RNNs and got another 10%. Now we're doing this with graph neural networks and so on, and transformers and attentive attention employing data structures in the future. So of course, it's really sometimes difficult to understand what works, right? We have to try it out because in industry, you use it for one purpose, and particle physics, you want to use it for something else. And we're trying to find analogies. So it's a bit of a challenge sometimes. Now, just to advertise, if you want to browse a bit through various papers, what we want to do in terms of graph neural networks is very nicely described in this paper that's available on the web. And what we want to understand is how to use the graph neural networks that were basically developed by sort of, let's say, social network studies in terms of Facebook. You know, what can I identify the group of people I can sell this particular object to or advertise this particular thing to? And what we want to do here is and instead understand the relations between the, if you want, particles or signals in the detector and so on, and build on these relationships. And that's what the challenge is. So how to match one to the other. So the tools that can very nicely incorporate relationships into something that we see in a detector. And it works, but we have to be careful about it very, very often to do it properly, and then really gain some additional knowledge and information. So just to give you an idea, this is how what it looks like. So this is sort of a conceptual plot, right? This is the actual analysis case. For example, using the deep neural networks, here you have the score, and then the colorful histograms are the simulated predictions of what the background would look like on one hand, and these here, for example, are what the new signal would look like. And as you can see, the score pushes the known to one side, the unknown to the other side, and then the crosses or the dots here with the error bars are the data. So we try to then, of course, understand how our predictions, our calculations actually match the data, and that's where the advanced statistics comes in. And just to stress a point, what we learned here is that the most complicated tool is not always the best, right? This is an interesting point in machine learning. You really have to try out a lot of tools to find what matches your problem best, because very complicated deep neural networks with a lot of data structure, and if you want slow, have a similar and sometimes even worse performance than something called boosted decision trees, which are much simpler and much faster structures, but perform as well, if not better, in many of such cases. Now, reasons are complicated, but this is more or less the idea or if you want, a warning on the proper use of machine learning tools in physics. So the latest greatest now, to advertise for another paper that came up early this year, we're looking into the use of transformers and other advanced tools. So this is a very nice study here that I'm flashing because it actually indicates the use, so this is the area under curve depending on the training epoch. So it compares the efficiency between simplest and then more and more complicated tools, right? And one can see that simple tools are not bad, that if you use more complicated tools, you can get you don't necessarily get a better result, right? This is, for example, the boosted decision tree. The red one is the convolutional neural network, which on paper should be better or is a more advanced tool, but it just doesn't perform as well necessarily. But if you use transformers, for example, the latest greatest, you can gain a lot. And even more, another point to note is that we learned is that you still need to incorporate as much of the prior knowledge as possible, because this gives you a jump from here to here. So if you teach the neural network what you already know, it sounds simple, but it's a lesson, right? If you teach it what you already know in terms of physics, which interactions are possible, which are not, which are the most complicated variables that you came up with in the past, if you want, manually, then the neural network will build on that, right? Just the approach that is common in industry will give it all the data and just wait what comes out. Turns out not to be optimal, because it's anecdotal, but it's an important lesson. For example, when we tried it, we discovered that the neural network very efficiently reproduced a specific variable that we came up with 10 years ago, right? So yeah, it validated our existing knowledge, but it didn't add to that, right? So then we added that variable in, and then it built up on that. So this is an important thing. So you have to sometimes get your hands a bit dirty and dig into the code and augment the loss function if you want with prior knowledge. It's not just binary cross entropy. You can add, for example, this has to be positive, or this shouldn't deviate from that much, or this variable I know, and what's the deviation from that, and so on. So this is an interesting lesson just to show how active this field is. And then here you have different outcomes of these scores. So the orange is the signal on one hand, and then you have the various backgrounds, the known stuff on the other side. And you can see that the performances are very different, right? And the shapes and so on. And then it takes a bit of thinking on understanding why and how and what's optimal for you. So to sort of summarize the caveats I already mentioned, the algorithms we used were really were developed and are still developed for the industry. We can contribute and we want to contribute. Sometimes we actually manage, but of course there is a lot of, if you want, manpower behind the industry. So we're often just trying to adopt what they developed. And we then, of course, try to follow the latest trends like using transformers, then anomaly detection was a buzzword for the last few years and so on. But again, when the smoke clears, when we implement everything and look at the output, we really need to understand what's going on, what's gone wrong usually. And it's really important to understand that these tools were not developed for the same purpose. So there is added value in terms of what we want to do and how to employ these tools in new ways. So another point is that we really need to also prepare the data properly. That's also now a separate topic, right? On how do you scale, rescale, transform, and so on the data before you put it in neural network, so it's most sensitive to the machine learning algorithms. Because remember, the neuron function is something very simple. It takes a linear combination of your inputs. So if they vary by scale, by like 10 orders of magnitude, of course, nothing useful will come out, right? Again, it's a lesson that you need to learn. And again, this is, I mentioned before, there is actually a paper from the 1996 by David Wolpert that sort of proves or demonstrates that there is no free lunch in terms of machine learning. So there is, you can actually show that if you have no prior assumption about the data, no model is a priori guaranteed to work better. So you really should take everything that's on the market and try it out. Even if the industry said, yeah, we don't like this because this is more performant, it might not be the same for your case. And this is all the things that we've learned at CERN when we try to implement the machine learning. Then another interesting point, apart from categorizing, saying this is good, this is bad, right, is to better understand if you want, the bad part or the non-interesting part, because of course we need to understand what we know or how the known stuff looks in our detectors really well to separate it from the unknown. And then an interesting case is that we can use machine learning to correct the background predictions. Now, why? For the for the background predictions, and also for the signal, we use something called Monte Carlo simulation, right? So we simulate what's been going on in the detector so that we have control of what's been happening since the beginning. And we say, okay, so this was like an interaction of producing like top quarks, and this looks like that in our detector. And then we can take this away, subtract this from the data. And sometimes, like in this case, for example, this is supposed to be a known process. It is, right? Just the interactions in the detector are very complicated. So when we want to reconstruct what's been going on, it turns out that the simulation that we employ sometimes poorly describes the data just because of the detector effects and so on that are really hard to take into account. And then, of course, we have to be careful, right? Because the discrepancy between the data and the, if you want, known can be either poor simulation or new physics, right? And this discrepancy shouldn't be, in this case, new physics. We need to correct the background. And here we can use machine learning to a great effect, because in essence, what machine learning is you give it a set of data and say, learn something from this data, and then employ that on another set of data. So this is exactly what we do, to put it simply. We give it a part of detector data that works well, and say, learn how this detector description, if you want, works in this case, and then employ this on such a set of data that it corrects for what we mismodeled here. And this is now all the rage, really. So what we basically, again, what we do is we employ different kinematic regions, if you want. So we take a separate piece of data that looks very much like what we want to study, but is distinct, and we train the neural network there, and then we employ it in something called the signal region, so the kinematic space, if you want, where we're looking for new physics, to apply the corrections. And these are usually then some sort of weights. And you can see, for example, in this case, that it really works really well, right? And this is a sort of multi-dimensional correction function that works for such cases. And then, of course, we understand what's been going on with our detector much better. And then also we also better understand the backgrounds and the signal, and we don't make any mistakes by claiming we discovered new physics when we really haven't. So this is one thing. Now, I mentioned, so correcting the simulation, right? So far we said, okay, categorization, signal background, correcting the background, correcting the detector effects. And then we can also, instead of correcting the simulation, try to do a different kind of simulation. So as said before, right, this is sort of a schematic thing we do at the LHC for data analysis. So on one hand, we have the detector, and then we do filtering of the data. We don't save all of it, just the one that looks interesting. We reconstruct it, we calibrate it to get the optimal output. And on the other side, we produce these simulations that we compare to the data, right? To separate, if you want, the known from the unknown, the signal from the background. So we need a lot of these simulations. And this is, in terms of LHC, that's half of our computing is just producing simulations, right? Which is sometimes, as an anecdote, hard to explain to the funding agency why you need that much CPU time, to just simulate collisions if you have them in the detector, right? Of course, that's a controlled experiment where you try to match A to B. It's a very complicated mapping between what's been going on inside the interaction and what you recorded with the detector. That's why you need to simulate it. But then, of course, these simulations are expensive, and you need a lot of statistics, right? You need much more of simulation than the data so that you have accurate predictions. Yeah, if you have poor statistics, then the information is vague, yeah, to put it simply. So you need a lot of these simulated events for high accuracy. And as mentioned, we need a lot of computing power. What we do is we use something called a worldwide LHC computing grid, WLCG, and that's a great success story. So we connect all kinds of computers across the world, including Vega and other clusters across Slovenia, in a common network, if you want, where we then push the data, get it processed, get it analyzed, we push it around and so on, and it's really put across the world in about 160 sites, and we have like 1 million CPU cores and an exabyte of storage, and it's just barely enough. Yeah. So the thought was then, can we use machine learning in any way to improve on this? And it turns out, yeah, we can. Now, so the idea here is, if we look at what's been going on, the detectors are very complicated, right? And if you want to simulate every wire and every response there, it takes a lot of CPU. So, but in the end, what we get out are, for example, these kinds of interactions that are basically look like images, right? So the idea is, okay, can we, like this has become common in the last few years, can we create these images ourselves? So, of course, this looks like using, convolution neural networks and image generation using machine learning. So the same that's being used in industry. But there are details. So here's an example I like to show, which is a video from NVIDIA, where they basically taught the neural network to generate faces, yeah, of people. So they gave it like 10,000 face images and then said, okay, make new faces from that. This is the sort of a simple example of image creation, yeah? So here, of course, the faces look quite credible in terms of, yeah, they look human, they have 2 eyes, a nose, teeth in the right place, and so on. Yeah, but of course, it's machine learning generated. It's not always perfect, right? Here is an example that escaped me. I wasn't fast enough. But in some cases, for example, it doesn't work well, right? And then this is something that we want to do as well in particle physics. And it's interesting, right? How this improves in terms of CPU power and algorithms and so on. This is just an example of the time the neural networks use to learn this kind of thing. And then the additional point is that what you see here is not morphing. It's that machine learning learns a function, right? If you have a z-axis, and then if you change the z coordinate, basically the faces change. And that's very interesting in terms of what we want to do for our machine learning as well. So this is just an example of what works in the industry, right? But of course, saying this works in industry is not necessarily the same as saying it works in particle physics. So first thing that you need to look at is the state of the art that currently exists in terms of so-called generative tools or models. Yeah, commercially, this is, okay, ChatGPT, Sora, DALL-E, and so on. And then we want to use this, right? And we try. So we use the various architectures like GAN, adversarial training, variation autoencoders, flow-based models are now popular, and especially diffusion models, and then attentive transformer models and so on. So basically, these are, again, simple algorithms, but what we want to do is getting something from a known shape to an actual shape that we measure in the detector that can be really complicated through this kind of algorithms, and then, which means we can, by transformations, produce any sort of data, yeah, from basically random noise, yeah, using something called probability density function, so a function that the generated, the machine learning algorithm learns. Yeah. So again, this is in terms of what the industry. You need a few lines of code, yeah, to produce something like an image here, which is okay, credible. Yeah. So the question for us, and that's now really a hot topic, is what is good enough in terms of physics. So, okay, these all look like hamburgers. These are credible birds. Those were credible faces, and so on. The tools were designed to do what, were designed to be useful in the industry, and they don't care about the error estimation, our biases or stuff. There is even no tools developed by the industry. So what we want to do, for example, as said, right, is use these most advanced tools. This is an example or two examples of the detectors to generate the data, learning on either data or simulation, and then using machine learning to produce more of this data. Same, like we don't give it faces, we give it collisions, for example, images, and say, now give us another image. Yeah, and then we try to get as good a match as possible to what we know is good enough. So Jean 4 here is basically the standard simulation, as we call it. And then this is the reference. And then with various tools, like using the most advanced diffusion models or generative networks, we try to match that. Yeah. So as you can see, the match is not bad, right? The question here is, of course, scientifically, which one is good enough? Because, a face looks like a face. There is no criterion except of it doesn't have 3 eyes, right, to make it really credible. In terms of using it for our simulation, as I said before, we really need to model the physics that's been going on very accurately. So the question is this good enough? And the general answer for this cases are just barely, right? So the Atlas experiment has an option of using the fast color GAN, machine learning algorithm, and this kind of match is considered just barely acceptable. Now, why do we want to use it as such? Because, as said, simulation is slow by design, the traditional Monte Carlo simulation. If you use machine learning tools, then we profit from all the commercial developments that we physicists or scientists in general, apart from computer scientists, really don't know much about, which is efficient programming, right? But Google or Facebook and so on that make these tools like PyTorch and TensorFlow and so on, so machine learning tools use this employ these techniques very efficiently so that they optimally run in parallel on GPUs, accelerators, and so on and so on. And they use the supercomputers to the best effect. To persuade the software you wrote to work in that way, right, isn't a real effort. So, of course, we're trying to adapt our software to these modern architectures, but if you use machine learning, we get it for free. So it's really this kind of machine learning simulation is like 4 orders of magnitude faster than the traditional simulation. So it's, if we manage to get a really good match, it's a real game. And okay, as said, right, this is a developing field. That these sort of plots were shown at the Computing in High Energy Physics, the biggest conference on computing in our field a couple of months ago in Krakow. Today was also showing this kind of studies that he's doing in terms of SMASH, as a SMASH fellow. Then we're coming to another topic where CERN is also very good, and that's actively contributing, and that's putting machine learning algorithms on a chip. So at LHC, we use state-of-the-art electronics. We've been contributing to the development in the field. And now what's all the rage is putting neural networks on the programmable hardware. So instead of using a CPU, we can use a FPGA, where we can basically, if you want, bake in a machine learning algorithm. And this makes it really, really fast. Now, why is this important? Because if we can do this, then we can use machine learning at the earliest stages of data analysis. So when we actually retrieve the data, if you want, trigger filter, when we immediately after collisions try to sort out what we really don't care about and won't even put on tape or disk, and what we want to preserve, then now we're doing simple checks, right? Energy is greater than. But if we can program chips with machine learning algorithms, this becomes so fast that we can use this already at these initial stages of filtering. And so that's really important, really fast response. And it's an ongoing effort. So both experiments are trying to put this neural networks on these programmable chips. And real time means we can use it for data filtering during the actual collisions. And okay, it seems to work, right? And this is something that we're building into the next generation of hardware that we're going to use in the upgrades of the detectors. So this is a good development. And then an interesting point is that this is basically something. Okay. We don't need the sound. That we can use to a great effect to collaborate with the industry. So to use this, the same thing for example, self-driving cars is a good example, right? Why? Because here you also need a very intelligent and very fast response in terms of a oncoming vehicle or bird or an obstacle on the road and so on that the machine learning algorithm needs to, or a smart algorithm needs to identify. So this is then something where we can, for example, collaborate with industry, as said, using these programmable chips. And that's a nice example of what we can do. So the basically an additional thing that's worth mentioning more towards the end is that we have an additional match in terms of machine learning and quantum computing. Because, for example, Google is working on basically the two topics, right? On quantum computers on one hand and machine learning on the other. So some enthusiasts, if we could call them like that, or very capable programmers, have been putting machine learning tools on quantum processors. So we can use the new quantum computers for machine learning, which is basically sort of a low-hanging fruit, right? So if you want to try out how to use quantum computers for high-energy physics, the simplest thing by now currently is to use machine learning and try to use machine learning in a bit of a different way, because there are different limitations and advantages using it on quantum computers to, again, for example, reconstruct what's been going on in the detector. So this has been a huge activity at CERN, also at DAISY, at smaller experiments like LUX, they've been looking into everything from vertexing to tracking and so on, using quantum computing machine learning algorithms. So this is, again, a hot topic. If you want, there is a nice summary of the activities from last year. And this is, again, something that we really want to look into because this is, of course, a new tool that's coming on the stage. And it takes a while to adopt to any new tool, right? So it will take a decade to use quantum computers optimally once they arrive in full power, same as we used a decade to use supercomputers, quantum computing, graphics cards, and so on. So that's why we always plan quite a lot ahead into particle physics. And the latest, greatest then, that's a hot topic. And there will be a separate chapter also connected to it in the new European planning for particle physics, is use of the AI, so more artificial intelligence in broader terms, in various aspects of the design. So actually using, the advanced generative aspects, if you want, of machine learning to, for example, design the experiments, so parts of the detector, or design an analysis, or design an optimal variable, and so on. So we're looking into the AI-assisted workflows on various aspects of this. Because, for example, like a good case that I've heard is, we think in terms of stages. We build, for example, when we build a detector, we first build the sensor array, right? And then we add the cabling, cooling, electricity, and then this needs to be put on a support and in a building and built somewhere, right? So it's all modular, and it's not in terms of space or use necessarily optimally connected. Yeah. Usually at CERN, the engineers always say that the physicists forget about all the cabling that's needed, right? So can you teach a machine learning algorithm to sort of integrate this together in an optimal way? Sort of glue the cooling on the sensors, build the powering and network and so on in the support infrastructure and so on in an optimal way. Why not? Especially if it's, for example, power and energy saving these days, right? It's an interesting aspect. As said before, right, we need to really plan ahead. And this is just to give you an idea of why we're planning ahead. These experiments are complicated and they take time to build and prepare for, and then, of course, use. And we are currently looking on this sort of timescale, right? So the FCCHH, the Large Future Circular Collider that's supposed to be built or is now in planning stages to be built as an upgrade to the LHC, right? 100-kilometer about circumference, maybe a bit smaller, around Geneva. This is really geography limited, right? Then here is Jura Mountains where you can't go much underneath. And we'll have protons colliding here at, sort of a order of magnitude bigger energy with much more data, will come only in the 60s, maybe, right? Okay, the wish is before, but realistically, things take time. This looks sort of far-fetched, but it's been the same story with the LHC, right? If you want, the World Wide Web, right, that was built in the 90s, was actually made for the LHC experiments, because this was the first case where the United States, for example, and Japan and so on were participating. So just communicating through Europe was not enough. You needed a better tool to pass more information in terms of images, data, and so on across the world. So the LHC was planned already in the 80s and then expanded and built in the 2000s, and it's operating now, right? So it's not a new time scale. This thing's just complicated. And it's interesting because you're always trying to hit a moving target, right? We have to plan now what kind of computing and software and so on we'll have in the next decade or in the next 30 years, right? That's why we're talking about everything from machine learning to AI to quantum computing and so on. And we have to, in order to be prepared and not to be surprised, if you want, or cause unnecessary delays when trying to do new physics in these newly built experiments. So basically, to summarize, we're trying very hard to get involved in these tools, gain expertise, collaborate with the industry and back. So there are a lot of schools, workshops, boot camps, as said, postdocs. SMASH is one of those, right? We're participating to a great effect. And it actually turns out that this collaboration works quite well. And it's actually communication of information and people goes in both directions. So it's not just, physicists going from CERN to Google. People get bored at Google and come back to CERN because we're doing interesting science. Of course, we need to be careful that this interaction becomes, remains, strengthens, and becomes more and more prominent where needed. Okay, this is a nice case that Lucas Heinrich usually shows that I'm just sharing here. So if you look at these timescales, right, you really need to think big, because from the web in the 90s, right, in 10 years we had Google, and now we have, like, in 25 years we have Wikipedia and everything on the phone and so on. In terms of machine learning, we started with deep learning in 2012, for example, when the first GPUs were used. That's sort of a, moment when we were actually able to do deep learning. So use supercomputers. In 10 years, from that we had ChatGPT. So planning ahead, what will we have in 25 years? Well, it's a good guess. It's good to guess to be able to sort of plan ahead, right? Then, as the last slide, what I like to show is what the question of what we'll actually find in the high energy physics. Now, it turns out that all the experiments that were actually built and operated found something interesting. Yeah? There are very rare cases where the experiments themselves didn't find anything new. But if you look at this is a good example of the most prominent, if you want, experiments. It wasn't always, or if you want, mostly what they were actually designed to do. Yeah. So Super Kamiokande is a good example in Japan, right? It was built to detect proton decay. This is a reaction that we look into to understand the creation of the universe. So is proton stable or not? Actually, we know that it's very stable, but how stable? So, and what they instead found out was neutrino oscillation, so massive neutrinos, something completely different that we didn't expect, right? And same for the other experiments. So we were looking, some were looking like Fermilab neutrino physics, and instead found heavy quarks, and so on and so on. So here the punchline is, if you don't look, you won't find. But in particle physics, if we look, we always found something interesting. And that's also the idea that we want to follow up with the optimal use of our machine learning tools, for example, in the future. And that's it for me. Thank you.